It's my unbelievable pleasure to introduce our next speaker, who is no one else than Katelynn Amanda Perrault Uptmor. And she's from William Mary. You probably know her, you've seen her before. She's our committee chair, and she'll be talking about GC output data.
Testing. Perfect. Okay. Hi, everyone. My name's Kate, and I am from William and Mary, as Peter just mentioned. I'm going to switch it up a little bit and talk about something completely different than maybe you're used to hearing at a conference like this. I haven't presented at the multidimensional chromatography workshop since 2018. Because we've been really busy organizing things, but this year I really wanted to show you some of the recent work that we've been doing because it's a little bit out of the box. I'll also say at William & Mary, my research group is mostly undergraduate students and the odd master's student, one of them is here. And my prior institution, Chaminade University of Honolulu, my group was also primarily undergraduate students. And the really cool thing about working with an entire research group of undergrads is no matter what crazy idea I have, they have to tell me it's good. Or maybe they're a little bit scared of me to say that. That sounds a little bit weird. So this project came about out of kind of a crazy idea that I have that NSF ended up funding, and I was really surprised about. So I just want to share a little bit about this project today. And I'll first off just also shout out Clarissa Kamara right here, who is the primary researcher on this work. So we know that communicating our results is really important, right? We've talked a lot about this already this week, that how we communicate with the rest of the world about GC is really an essential component of what we do. And comprehensive two-dimensional gas chromatography, or GC has been proposed for a lot of different forensic applications. And my group really focuses on a lot of forensic applications. And here's some examples of where gas chromatography is used. But there's been a lot of active research in GC in these areas. So this brings us to kind of the idea that spurred this project, really the idea of a debate between two sides. So on the first side of this debate, we have more of the forensic science field who say things like GC MS is too complicated. It will never be suitable for routine analysis in forensic science. That expert witnesses are never going to be able to explain this incredibly complicated data in a courtroom to people like judges, juries, and lawyers. And GCMS has always worked just fine, so why would we bother changing? Some of these things might sound familiar to some of you. On the other side of the debate, there's people like us, people who come to the multidimensional chromatography workshop who say GCMS provides substantial benefits for non-targeted profiling. And GCMS provides more like images as an output that could be really helpful for lay people to understand the data that we're trying to present. And that expert witness testimony, and I've heard people talk about this in the past, could or would be more effective if we were to use GC data than if we were using one-dimensional GC. So on one side, we have people saying, go away, we don't need you. On our side, we're like, we're really awesome, we love this. And then there's me in the middle that comes from both a forensic background and also an analytical background. And I'm kind of in the middle looking at this argument going, I see the valid arguments on both sides. I really do. I think that there's valid arguments to be made both ways. So what is the idea? So who's ever played one of these spot the difference games before? Yeah, okay, cool. And immediately, the moment that I put this up on the screen, you didn't even want to put your hand up when I asked you that question because your eyes started going back and forth between these images, right? You already started comparing these images to one another before I even said a word. And we can do this with more complicated images as well. So here we have the Eiffel Tower. My students are going to visit it right after this conference. And we can do this with more complicated images, and this might get a little bit harder, but it's still kind of the same idea, right? And we're actually bombarded with these types of comparisons in our lives all the time. My husband and I just recently bought a house, and I get like endless ads about house renovations. So you can see this like before and after of a house that I screenshotted from Facebook the other day. All right. So when it comes to expert witnesses actually presenting evidence in a courtroom, oftentimes they are doing what we would refer to as comparative analysis, comparing one thing to another. Usually that involves a known sample and a reference sample, and you're trying to show how similar or different those two things are. And that can often involve presenting visual aids. These can be oftentimes things like photographs or maybe charts. And some studies have even looked at how people in a courtroom, if they're serving on a jury, can make more valid conclusions about things that are being presented to them if they see 3D images or 3D models of something compared to, say, like just a photograph. So that kind of got me thinking about the fact that our data is multidimensional and how this might be useful. But there really is like a huge, huge lack of information about how juries process information. If you know like any forensic TV show, you probably know that fingerprints and DNA are considered to be kind of like the gold standard evidence types. But chemical analysis is also presented in the courtroom all the time, and there's really nothing that's ever been done to think about how people perceive chemical data. So there's a huge gap in knowledge here. So the objective of our study was to provide the first empirical study of people basically observing chromatographic differences, especially when they didn't have a background in GC, or GCMS. We wanted to know if people were effective at identifying differences in two chromatographic profiles. In forensic science, you would use the phrases distinguishable or indistinguishable. We try to avoid the words like matching or not matching. And whether individuals were effective at identifying the degree of similarity between two samples. And do individuals feel that chromatographic data is hard to determine differences between? If they're looking at these profiles, is it hard for them? So subjects were asked to play a virtual spot the difference game without really any information surrounding it. So we took away the component of like a mock case in this very first study, and the idea was really just to present people with a game and see how they performed. So this is very different type of research than I normally do, I'll just say that. We've done work with human subjects before, collecting samples from people, but this is a totally different type of data to be collecting. So we had to get IRB approval and create a survey in order to collect this information from people. People were recruited by a number of different processes, things like emails, advertisements, and so on, and it's actually, like, it was quite challenging for us to actually get enough people involved in the study. We recruited from the university that I was at the time and the wider state system as well. And participants, in order to do the study, they had to meet jury criteria. So if you're aware, like at least in the United States, there's a list of things that make you eligible for jury duty, and so people had to be eligible based on those pieces of information. We were able to get 70 responses, which ended up being a little bit more than we were targeting, so that was really good. And basically what happened is people would fill out a questionnaire to see if they were eligible, and if they were directed to take this online survey. They probably had no idea what they were getting into at the time, but they ended up doing a whole bunch of different comparisons. Before they started doing their comparisons, we gave them an example just to kind of get them like warmed up and kind of used to the process. So we showed them two images and asked them to spot the differences, and then we asked them to answer a question. And I have to say, this was the hardest part of this work, was trying to figure out what to ask people. Because we did the initial survey, and we originally were like, well, we're numbers people as analytical chemists, so we'll just give people a percentage of similarity or difference and ask them to pick which one is right. And pretty much everybody came back and said, we have no idea what you're asking us to do. So instead, we tried to develop phrases that people would identify just to see like if we could improve that, and that worked a lot better. So this is what we ended up going with. So you can see the options here are like, yes, they're identical, no, and then with a qualifier. So no, there's a few differences, like maybe 3 differences, several differences, maybe 10 or 12. No, very many differences exist, so there's like a lot that they see different. And the last option is that they were completely different images. So if I showed you like an image of a cup of coffee and an image of a strawberry. Then we gave them the answer. So we showed them where the differences were and how that would be ranked according to the scale. And then we asked them to say how hard it was. So we asked how difficult it was to perceive the differences between the two images. And we ranked that as easy, moderate, and hard. Then, just for reference, the percentage differences that we were actually using for those phrases are listed up here. We kind of considered this to be either a match or a non-match. So like a indistinguishable option would be 0% difference. They were the same thing. And distinguishable was any of the other options, essentially. So we looked at the data both by percentage difference, but then also by this idea of distinguishable or indistinguishable. We also coded those with numbers just so that we could do statistics with them for both of the questions. Here's some examples of what this looked like when people were presented with it, and you can see the entire survey. It's published with the data as supplementary information. So here you can see this is an airport image. So we showed them pictures as well as a control, and then we showed them one-dimensional GC data, and we showed them GC data. In order to actually make it quantitative for the amount of difference, we actually photoshopped all of these to make their actual differences between the two so that we could actually quantify based on a grid or pattern system how many squares in that grid were the same versus different to generate those percentages. So moving into the data, this is the first result. So this has to do with how hard people thought these comparisons were. In general, people were very confident in their ability to spot differences. Maybe you feel like that when you play like the New York Times Spot the Difference. Most people ranked every single comparison as easy. Sometimes they would rank it as moderate, but it was very, very rare for someone to say that a comparison was hard. So that was really interesting. This shows you the comparisons that people thought were the absolute hardest. So here it's all images that are the same. So probably people spent more time and energy trying to identify differences between those before they made the judgment call. This is the hardest GC comparison that people ranked, a 1.6 out of 3, so still between easy and moderate. And again, you can see that it's a 0% difference plot. This is just kind of a fun fact and something that we tried not to focus on too much, but there were 45 comparisons done by each of the individuals, the 70 people, resulting in over 3,000 comparisons done total. And there was only one question where people were able to all get the answer correct, which is amazing that there even was one, and it was a GC contour plot. It was like a win for us, but we weren't trying to focus on it too much. Not statistically significant. So if we were to look at this broken down by image category, there was really no significant difference between people's ability to compare non-chromatographic images, one-dimensional GC plots, and contour plots. And you can see that the percentages are like between 52 and 67% in terms of the accuracy. If you break that down by category here, you can see that even though people thought it was really challenging to compare images that were the same, that's the 0% different category, they were really good at it. So they were really good at getting that answer right, even though they thought it was hard, which is kind of interesting. In the middle categories, where there were some to many differences, people were generally less good at seeing the exact amount of difference. That's probably because your ability to say whether something is few or several or many is kind of subjective, right? And then if we actually start to break this down by whether people were good at telling if something was distinguishable versus indistinguishable, they were much, much better at that. So if you look at the black bars over here on the right-hand side, these are the same bars as up here, but the gray and the white show you match versus non-match, essentially. So they're really approaching 100%. So people were actually quite good at making that clarification. So there's a lot of questions that we generated in this work. We would really like to increase participation, get more people involved. We'd also like to present data to people with like an actual case scenario so that we can have them kind of understand what it is that they're doing, why they're doing that. We also really just kind of picked one color scheme and one plot type, but we know in the GC community there's many other types of plots we could have presented people with. And color is something that we think about a lot as well. We used a white background with blue blobs, and of course there are other color schemes out there. So if we were to change it, would that have an impact? We're also really intrigued by the idea of seeing if we can get AI to make these distinctions. It makes a lot of sense to go in this direction. But it's more of a curiosity, and I doubt that right now we're in a situation where AI is going to be replacing juries anytime soon. So in conclusion, participants were generally confident in their ability to compare these images. Most were challenged by the comparison of identical images over ones that actually had differences. That could be due to large time effort that they had to put into that comparison, but they were really good at it even though they thought it was hard. Not very successful at quantifying the amount of differences between plots that were distinguishable from one another, but they were really successful at determining whether two plots were distinguishable or indistinguishable. Overall, we found that there's no significant difference observed between performance across our 3 treatment groups. And so my kind of takeaway from this study is that current data supports that GC-GCMS data is no more or less challenging for people to understand than GCMS data. And I want to just acknowledge our funding agencies. If you're interested, I can share the link to the full paper with you as well. And I want to thank the committee for allowing me to present my work. Thank you.